Well, hello, this is Dr. Keith Schubert with our final video lecture on floating point ones. This one I want to talk a little about floating point instructions in MIPS. Um, just as a note to you, this is usually done on a coprocessor. So what will happen is there'll be some transfer instructions that'll carry over, and then specific instructions that have to be different from standard MIPS, which is integer, to actually be sent to the coprocessor. So by default, the floating point hardware is coprocessor 1. So you can actually have multiple coprocessor that goes in. So that is the first one that goes in. You'll often see this letter C in floating point commands because they are coprocessor commands that are in. There are a complete separate group of registers. Most of them are set as 32-bit registers, but you can pair them up. F0 and F1 become a double precision register all the way up. So you can, either get half as many double precisions or, the full amount normal of single precisions. The second release of it supports 32 of these 64-bit ones that go in. The instructions only will work on these floating point registers. Notice F0 is not predefined as 0. And they don't generally do integer ops on floating point data or vice versa. So, if you want to do an integer times it, you have to encode it as a floating point number. More registers with minimal code size impact, go on that. So it's a reasonable trade-off. So when you take a look at this, remember I was telling you about the coprocessor C. Load word to the coprocessor 1. Load to coprocessor 1, store word, coprocessor 1. Right? The D is, technically this is actually load double, store double, coprocessor 1. And it's, other than that, it follows the same thing. What is the destination to it? And then displacement R offset. So this is stack pointer plus 32. This is telling you they're doing a load from the stack frame into that. And that's fairly normal if you were you could store a value from the main processor onto the stack and then let the coprocessor pull it off. So notice we do have a difference between single and double precision. The way you can tell is the S at the end. So this is single precision that goes in because it's add single precision, subtract single precision, multiply single precision, divide single precision. Other than that, it's the same. And then for the double precision, it's obviously just got the add, double, subtract, double, so on and so forth. And again, destination first and the rest carries in. You can also do comparisons, so compare, and then the 2x code here tells you it's the old Fortran codes, which got carried into C. So equal, less than or equal, right? There's GT greater than, GE greater and equal, blah, 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 NE not equal. So these are our standard stuff. What's different is, as opposed to writing these into a register you have to use up, these are now big floating point registers. That's a huge waste to us. What they've done is they've added condition code bits, and a lot of machines just use condition code bits anyway, and so it'll store the result of this in a special purpose register called a condition code register. And it's usually part of the status register for the operating for that particular pipeline. And so it just takes a couple bits. There are a lot of machines that will actually, without you even have to do this, you just have to do compare. MIPS doesn't do it. And then it actually has a bit for less than, for equal, and for greater equal. If they're all not set, that'll tell you different things. So the combinations will let you go in and compare them. And then you can branch on these condition codes using branch for coprocessor 1, right, as it goes in. And then you have a target label, and so you branch it whether it's true or false. And that's based on what is the condition code bit that was set for it. So branch on coprocessor 1 if it's true, branch coprocessor 1 if it's false, and it goes to this label. You don't need anything to check because it automatically uses the condition code registers. So let's take a look at what this is. is a kind of typical Fahrenheit to C command. So the C code, you'd be returning a float. We call it F to C, right? Fahrenheit to centigrade. You get Fahrenheit coming in, and it just returns, 5.0 divided by 9.0 times Fahrenheit minus 32. Just as a comment, this is technically correct, but I don't like it as much. It's actually better if you do this and then multiply this number times 5 and then divide by 9. The reason is, as long as you don't overflow, gain the biggest number before you divide allows you to actually guard more precision. You'll be safe in IEEE, that's why they give you those extra bits, but it's, in my opinion, always a better programming practice to try to do that, which will preserve things as much as possible. Now, what they're saying is they're going to stick Fahrenheit in floating point register 12, assume that was already done, and they want you to put the result that you're passing back in floating point register 0. And they say that the literals are in global memory space. So that's what this GP is. This is one of your standard registers that's in there of the base 32. This is called the global pointer, and it points to where your memory space is. And then they've assigned some constants with labels that tell you constant 5. So this is a pointer to where 5 was stored inside the global space. Constant 9 is a offset pointer from the global pointer that stores where 9 is, and constant 2 stores where constant 32 is a pointer from the global pointer that tells you where the number 32 was stored. So these are those constants that are there. So what they do is they first, load in these two right into 16 and 18, and then they divide them. So that just gives you 5 divided by 9, and they store it in here. So that's 5 nines. And then they load the number 32, and then they're going to take F12, which is your Fahrenheit value, minus 32, stick it into here, and then they'll take the 5 ninths you calculated earlier, 5 ninths times Fahrenheit minus 32, and they put in F0, and they jump on a register the return address. Now you'll notice some of these commands in here are commands that use the registers that are in the base 32. This is a standard command. A lot of these are the floating point commands that go in. This gives you an idea. You don't have to actually write a lot of code like this, but I figured it was worthwhile to see it. The big trick to this that's in is IEEE 754 gives you a way to get accurate things. So this is just kind of an overview of what I mentioned a little bit earlier. There are 3 bits of precision that are extra beyond there that they use to make sure you're safe. The guard bit, the round bit, the sticky bit. There are different rounding modes that are available. Usually the standard one that is used is, half the time you round up at the midpoint, half you round down. So you do rounding for everything. But if you remember 0.5, the standard rounding says always go up. Well, the problem is that actually means there's a disproportion of round-ups. So there's actually a round mode that lets them go up half the time and down half the time. It turns out that cancels errors a little better. But you don't have to worry about the rounding modes right now. If you go into a numerics course, they'll talk about them. I just want you to be aware and to give you an example of where that is and why. So it allows you to fine-tune the behavior of it. And it is worth noting not every unit implements all of 754. So particularly once you come to the newer standard that goes in, there's a lot of specialty instructions and other things. So if you do the base stuff, you can actually say you're compliant, and there are some that implement all of it, and that's when you have really nice stuff. So there's a trade-off between the complexity, performance, and other things of that sort to make sure that you get them. The area, why do we care about this? Scientific code, which is my area, is very important. But another classic example is banks and stuff. If you've got some tiny little errors that go on, you might think, who cares? But over millions of people's accounts, that adds up to a lot of money. And then this is in the 90s. There was this famous, Pentium bug problem that happened with floating point division, and this created a huge issue that came around. And so that the Pentium bug, it was actually shown that it happens even to common people, and it caused some quite a bit of problem for people. But it also gave some funny jokes like, how many Intel Pentium designers does it take to screw in a light bulb? And the answer is 0.999375. Sorry. But it creates some issues on there. Now, in addition to floating point and integer, there's actually, for like graphics and audio, you don't actually use that much of it. So what's typically done is they'll break up other things into little sub areas. And they'll break a 128-bit number into different little groups. And, that allows each of those to be handled in parallel. We just break the carries between them and they become independent numbers. And it allows us to use them. And for a lot of things, you have 8-bit color or 16-bit color or 32-bit color. That allows us to do those in parallel, and you can calculate your graphics faster. And that becomes an important issue. So that's another kind of number that, or number representation that becomes very important and has turned out to be crucial for calculating things. And it illustrates one of our parallelism ideas that goes on, which is a single instruction for multiple pieces of data inside them. So this is an example of where that type of parallelism comes in. So I should give you enough that you can understand chapter 4, or I guess it's actually chapter 3. In any case, it gives you enough you can handle all of the fun stuff from there, and then we'll pick up with the next stuff in class. So have a good day, and I'll see you in class.